Hi, welcome to this session. I'm Min, a senior staff engineer at LinkedIn and the tech lead for the LinkedIn Spark team. So together with my colleague Chen Li, another member of the Spark team, we're going to talk about Project Magnet, which aims to drastically improve the performance and the scalability of the shuffle operation in Spark. And it will also be an upcoming feature in a future release of Spark itself. I hope you will find this session useful. So we will start with a brief overview of the Spark ecosystem at LinkedIn, and also talk about the major challenges we have faced with operating Shuffle at LinkedIn scale. And following that, we will also introduce Project Magnet and the push-based shuffle mechanism it brings to the Project Spark. And also to demonstrate its impact at LinkedIn, we'll also share the production results of Magnet and some of the key learnings we have gathered. We will conclude this talk with a few interesting areas that we believe Magnet can bring further benefits. So after evolving over a period of 4+ years, Spark at LinkedIn now represents a pretty massive scale infrastructure. Across our two largest and busiest clusters, we have more than 11,000 compute nodes. Every day, more than 40,000 Spark applications are submitted and running on our clusters. These Spark applications contribute to more than 70% of our total cluster compute resource usage and generate close to 18 petabytes of data to be shuffled on a daily basis. And this massive scale infrastructure also grows very fast. We have seen more than 3x year-over-year growth in our Spark compute footprint for the past 2 years. So when operating such a massive scale infrastructure, many challenges can arise. Among these, the ones associated with the shuffle operation is perhaps the biggest we have dealt with. Shuffle is the very foundation of the MapReduce compute paradigm, and Spark's shuffle architecture perhaps represents the result of a continuous improvement over the past decade in big data compute engines. So as illustrated here, Spark adopts the so-called solve-based shuffle. Thus, each map task inside a Spark executor would produce one shuffle file consisting of multiple shuffle partition blocks for the corresponding reducers. The shuffle file is produced on local disks and managed by the external shuffle service deployed on the same node. When the reduce tasks start running, they would fetch the needed shuffle blocks from the corresponding remote shuffle services. This architecture achieves a reasonable balance between performance, scalability, and reliability for shuffle. However, when operating it at LinkedIn scale, we still encountered multiple issues. So the first one is a reliability issue. In our production clusters, we have noticed that the shuffle services can become unavailable during peak hours due to the heavy request load. This will result into shuffle fetch failures and leading to expensive stage retries, which can be pretty disruptive, causing workflow SLA breakage and even job failures. The second is an efficiency issue. At LinkedIn, we store the shuffle files on hard disk drives. Since the reducer's block fetch requests arrive in random order, the shuffle service would also access the data in the shuffle files randomly. If the shuffle block size is small, then the small random reads generated by the shuffle services can severely impact the disk throughput, extending the shuffle fetch wait time. The third issue is about scalability. An abusive job shuffling many small shuffle blocks could easily choke a shuffle service, leading to performance degradation. This not only impacts this abusive job, but also all the neighboring jobs sharing the same shuffle service. As the total number of Spark apps increase, more such abusive jobs will appear. And it's not always easy to tune these jobs to shuffle larger blocks, but whenever it happens, it will lead to unpredictable delays to other jobs that's otherwise behaving normal. So we took a look around all the possible solutions, and we noticed that there are a few existing optimizations that can improve shuffle performance by either reducing the need of shuffle or properly changing the shuffle partitions. Techniques such as broadcast join, caching of the RDD or data frame, and even bucketing are common ways to reduce the need of shuffle. However, they either have limited applicability or require non-trivial manual setup effort. Thus, they are not generic enough to solve these issues we have encountered at our scale. In Spark 3.0, the AQE feature, the adaptive query execution, was introduced, which enabled Spark to auto-collate many small shuffle partitions into fewer larger ones. So this feature could actually lead to slightly increased shuffle block size and result into better shuffle performance. However, in our evaluations, it is still not sufficient to address all the challenges we have faced. So facing all these challenges with Shuffle and the limitations of the existing optimizations, we realized that solving these issues actually require a more fundamental improvement to the Shuffle operation itself. For this, we have designed and implemented Project Magnet, a novel push-based Shuffle architecture. Magnet aims to merge small Shuffle blocks into larger ones, thus optimizing the I/O pattern during Shuffle. As part of this process, a second replica of the Shuffle data gets created, which helps to further improve the reliability of Shuffle. And more importantly, Magnet also aims to significantly improve the Shuffle data locality, which significantly boosts the performance of the Shuffle operation. So due to the time constraint, we won't be able to go into too much details of Magnet, but our paper describing the detailed design and implementation of Magnet was published in last year's RareDB conference. We will also provide more links towards the end of the presentation for people who are interested in knowing more. So now I will hand over to my colleague Chandni to talk about the high-level designs for Magnet, as well as its impact to LinkedIn's offline compute infrastructure.
Thanks, Min. Hi, I'm Chandni, and I'll be talking about the basic design principles of Magnet and its impact at LinkedIn. We have designed Magnet as a complementary approach to the existing shuffle mechanism in Spark. Since it works along with the existing shuffle operation, it is a best effort approach where not every block is guaranteed to be pushed and merged. As shown in this diagram on the right, the core idea behind Magnet is that instead of having reducers fetch small blocks of shuffle data from the external shuffle services, the mappers, after they generate the shuffle data, will also push the shuffle blocks to the shuffle services. The server can then merge the blocks belonging to a shuffle partition into a merge shuffle file for that partition. Since this push merge approach is best effort, the reducers now fetch a hybrid of blocks. As shown in this diagram here, the reducers will read both merged shuffle blocks as well as unmerged blocks, since not all blocks are guaranteed to be merged. When the reducers read larger merged blocks, then that improves the IO efficiency because the server can now perform large sequential reads instead of small random reads from the disk. Another benefit on the read side is that now the location of these merge files provide a natural locality preference for the reducer tasks. They have higher chances to be placed at the same nodes as the merge files from which they read the shuffle data. And this has a big impact on the cluster efficiency as it leads to more shuffle data that is being read locally. In addition, the overall reliability is improved as well because there is another replica of shuffle data that is created. In cases where reducers just fail to fetch the merged file, they will fall back to fetch the unmerged blocks making up that merged file. Now we will look at the impact that Magnet has had in our production clusters. We have rolled out Magnet to 100% of all the Spark workloads at LinkedIn. And we did some analysis and measured the data from our two largest production clusters. And currently, Magnet is serving 15 to 18 petabyte of shuffle data daily. When we rolled out Magnet to these clusters, we did it in stages with a ramping tool to minimize our risks, and we reached to the 100% mark without encountering any major issues. This is a big attestant to the overall reliability and scalability of Magnet. In addition, Magnet has significantly transformed the landscape of shuffle in our clusters. We have observed 30 times increase in the shuffle data that is read locally compared to what it was 6 months ago, as we can see in this graph here. The y-axis in this graph is the shuffle data locality ratio, which is defined as the percentage of the total shuffle data that is read locally. The x-axis are the days when this metric was recorded. we can see that as Magnet is ramped up during the last 6 months, the amount of shuffle data that is read locally has increased. Now, since Spark allows reading local shuffle data directly from disk and bypassing any network RPCs, the load on the shuffle service is considerably reduced. This helps a lot to improve the cluster efficiency, and it also leads to higher stability in the cluster. Specifically, we've observed an overall reduction of 84.8% in the shuffle fetch wait time across these two clusters. The shuffle fetch wait time measures the amount of time that reducers spent waiting for remote shuffle data to arrive. In this graph here, the y-axis represents the average shuffle fetch delay percentage, which measures the total shuffle fetch wait time as a percentage of the total task time. The x-axis are again the days when this was recorded. So we can see from this graph that as magnet is ramped up again, the average shuffle fetch delay percentage reduces. And this significant reduction shows how much magnet improves the overall efficiency of the shuffle operation in our clusters. In addition to improving the cluster efficiency and stability, Magnet also directly benefits the Spark jobs in our clusters. One of the key benefit of Magnet is that it doesn't require any job specific tuning. The users just need to turn on push base shuffle configuration and they will see improvements in their job. To quantify the benefits that Magnet brings to the Spark workflows, we analyzed around 10,000 workflows that were onboarded to Magnet, and then we measured their compute resource consumption and overall job runtime. Now, to measure the improvements by Magnet to these workflows, we had to compare the Magnet enabled and disabled executions of these workflows, which dealt with similar amount of data. After this analysis, we saw that the overall compute resource consumption went down by 16.3%. About 20% of these flows were previously heavily impacted by shuffle fetch delays. Heavily impacted flows are the ones which had non magnet executions, where shuffle fetch delay time was over 30% of the total task time. Among these flows, the overall resource consumption went down by almost 45%. So now for the improvements in the job runtime, we observed that 50% of the heavily impacted workflows had seen at least 32% reduction in their job runtime. This is also shown in the graph here, which is the percentile time series chart. A thing to note here is that this chart represents thousands of Spark workflows. In this chart, the y-axis is the app duration reduction percentage, which measures the overall job runtime reduction with magnet as a percentage of the total job runtime of non-magnet executions. The x-axis again are the days when this metric is recorded. The middle line is the 50th percentile of the app duration reduction percentage. The bottom line is the 25th percentile. And the top one is the 75th percentile. So for April 25th, the data point on these lines, they show that there are 75% apps which saw more than 23% reduction in their job runtime. 50% apps saw more than 38% reduction. And 25% of these apps saw a reduction of more than 58% in their job runtime. So, just to summarize, Magnus has resulted in much faster and cheaper job executions across our two production clusters. With the ramping up of Magnet to 100% adoption in our clusters, we've also validated some of our initial theories about it. One of them was that if Magnet is more widely used within a cluster, it will further reduce the load on the shuffle services, and therefore the shuffle performance will also increase. This graph here is the same as the previous one, but for a different time period when we significantly increased the adoption of Magnet in the cluster. And this helped us to validate our theory about magnet. From this graph, we can see that across the two highlighted windows, the first one where the adoption was increased from 12% to 60%, and the second one where it was increased from 60% to 100%, the app duration reduction percentage increased across all the percentiles. Just a thing to note here is that the job runtime in a large scale multi tenant cluster can be impacted by various factors such as delays in allocation of containers by yarn or skewness in the data. And it is not possible to exclude these factors in the job runtime measurements. This is the main reason we see regression and fluctuation in the above graph, and especially in the fifth and the 95th percentile. Since these are measuring extreme cases, they tend to have more fluctuations than the other percentiles. Finally, we also compared the performance of magnet with different disks. We ran a benchmark which shuffles around 800 GB of data on both NVMe and HDD. For this benchmark, we had set up two 10 node clusters where one was using HDDs and the other one was using NVMe disks to store the shuffle data. And we ran both magnet enabled and disabled benchmark jobs on these two clusters, and the results are shown here in this table. Without magnet, the benchmark on HDD took 16 minutes and on NVMe it took 10 minutes. With magnet, the benchmark on HDD took 7.3 minutes and on NVMe it took 4.2 minutes. What we learn from these numbers is that even though NVMe disk improved the shuffle efficiency, magnet just with HDD brings an additional improvement of 17 percentage points. Also, magnet on NVMe brings significant improvement compared to vanilla Spark on NVMe. So we can conclude from this that even though the shuffle delay problem can be addressed with a more performant disk to some extent, but the RPC load on the shuffle services also contribute significantly to this delay, and this problem is alleviated by magnet. So that brings an end to my section. I will hand off to Min from here. Thank you.
Thanks, Channy, for giving a good summary of the design and impact of Magnet. So now that we have achieved this internal success with Project Magnet, we also have a few areas that we're working on to bring the benefits of Magnet to even more scenarios. The first is contributing Magnet back to Project Spark. This is an ongoing effort under the Spark Jira ticket, Spark 30602, and we have already contributed around 50% of our internal code base. So once completed, push-based shuffle will be included in a future release of Project Spark itself. So in addition, in the past 1 to 2 years, we have also seen a few solutions from other big tech companies that aim to improve Spark's shuffle operation, such as the Costco shuffle service from Facebook and the Zeus shuffle service from Uber, and a few other solutions. So compared with these solutions, Magnet has a few unique advantages. The first is Magnet's native integration with Spark, meaning that no external storage systems or coordination services are needed to use Magnet. This has helped significantly at LinkedIn to ensure ease of deployment and monitoring, as well as making sure that we do not hit any unexpected scaling bottlenecks from these dependencies. The second is a much improved shuffle data locality that Magnet brings to the table. And we have already seen in Chinese section that how much this helps to improve the performance, reliability, and scalability of shuffle, even with SSD or even NVMe disks. So we hope that once Magnet becomes available as part of Spark itself, other people can also try that out and benefit from the much improved shuffle architecture. And we also welcome collaborations from the community on this work. And in addition to the open sourcing effort, we have also identified a few areas where Magnet can help to bring additional benefits. Specifically, we're seeing that Magnet can help to further optimize compute and storage disaggregate data infrastructure that's commonly found in cloud environment, as well as optimizing Python-centric data processing workloads in AI data pipelines. And we'll briefly talk about these two areas before concluding this presentation. So as more companies are embracing cloud to operate their data infrastructures, we have seen an increasing demand for compute storage disaggregate cluster deployments, where the datasets are permanently stored in remote storage clusters, where the compute happens within an elastic cluster on cloud. Such a setup helps to reduce the cost of operating data infrastructure on cloud, as compute instances can elastically come and go based on demand. However, there hasn't been a very good solution for storing shuffle data in such a disaggregate cluster setup yet. So one common approach is to just store the shuffle data on local disks attached with compute instances. However, this hampers the compute elasticity, since decommissioning the compute instance would also mean loss of the shuffle data stored on it, which can actually lead to expensive stage retries. This also runs the risk of exhausting the limited local storage capacity, as compute instances on cloud usually do not have ample storage space. The alternative approach is to just store the shuffle data in remote disaggregate storage in order to decouple the compute instances from shuffle storage altogether. This, however, also has a non-negligible performance overhead, since all reads and writes of the shuffle data now needs to go through this remote storage. So with Magnet, we're actually trying to propose an alternative hybrid approach for storing the shuffle data in such disaggregate cluster setups. So we will leverage both the local storage available to the compute instances and the remote storage, such that the local storage is acting as a caching layer for the shuffle storage. With this setup, the shuffle data will still be produced onto the local storage first. However, the local storage is now treated as an ephemeral storage instead of a permanent storage, meaning that the local storage can evict or even relocate locally stored shuffle data to remote permanent storage if needed. Thus, it can tolerate running out of local storage space or even compute instance decommissions. When the shuffle data is fetched, if it is still present in the local storage, it will be accessed directly. Otherwise, it will be fetched from remote storage first before serving to reducers. This approach would still preserve Magnet's benefit of the much improved shuffle data locality, while also enabling the decoupling of shuffle storage from the compute instances. We will provide links to more details on this approach at the end of the presentation. So in addition to this, another area that we see Magnet can bring additional benefits is how it can help to optimize Python-centric data processing workloads. The surge of the usage of AI in recent years across industry has driven the adoption of Python for building AI data pipelines. And different from the analytics use cases, where developers might still largely prefer SQL as the language, the AI developers are increasingly leaning towards Python as their first choice. Since Magnet's optimization is at the shuffle layer, which is a very fundamental building block for modern big data compute engines, it is generic enough to bring benefits to both SQL-centric analytics workloads, as well as the Python-centric data processing workloads in AI data pipelines. To fully unlock such benefits, we're also looking into supporting Magnet for Spark on Kubernetes deployment scenarios. So this concludes our talk. Towards the end, we also want to provide a few resources for people who are interested in knowing more details. The first is the upstream Spark Jira ticket, under which we're currently contributing Magnet to Apache Spark. You can follow this ticket to get an idea of when this feature becomes fully available in Spark. The second is a blog post we published last year, which talks a bit more on the design implementations of Magnet. And this blog post is also a simplified version of our VRDB paper published last year, which contains more insights. To last, we also recently published a second blog post, which contains information about the production results of Magnet at LinkedIn, as well as more detailed information on some of the future works we just talked about earlier. We hope you will find them useful. So towards the end, we would like to also encourage people to read and review this session and to let us know your feedbacks. We will also be available for Q&As after this presentation.